Good afternoon, everyone. Welcome to our the afternoon session. The first talk is given by Professor on Hiroshi Ooguri, and he's an expert on quantum field theory, quantum gravity, and some related mathematical topics. He's going to talk about exploring the conformal field theory landscape for the next hour. Let's welcome.
Thank you. Thank you for your kind introduction. So I would like to tell you a little bit about what I know about conformal field theory. So, I have become very interested in structure of conformal manifold, which is a family of conformal field theory. How to define distance and how to understand the structure. And there have been, in two-dimensional conformal field theory, there have been quite a few structures that we have learned. So for example, if you consider a two-dimensional sigma model whose target space is a circle, then it's a half line. And, but it doesn't start from radius 0, it starts from 1 because of interesting T duality. And in general, sigma model with Tn target space is a coset space. And I forgot to locally, it's a coset quotient of O11 divided by On plus On, but there are some discrete identification. If you have n equal for 4 conformal field theory, then locally it's again a coset. But if you have 2, it has some other interesting structure of special geometry. Little is known about higher dimensional case, but for example, for the n equal 4 superconformal manifold, we know it is complex one-dimensional since exactly marginal deformation is the top component of stress in a tensor multiplet. So if you assume there is only one stress tensor multiplet, it should be one-dimensional. And so, but the global structure is not known. And so the question that I would like to understand is that, is there any universal property of conformal manifold, regardless of whether they are supersymmetric or not? And so this was sort of motivated by what's called swampland conditions. So suppose you have conformal field theory, which has a weakly coupled gravitational dual. And so by that, I mean, in terms of Einstein gravity coupled to finite number of matter field in ADS, then there can be expectation from what's called the swampland program, which Cameron Buffer proposed 20 years ago. And I've just copied the abstract. So he said, it's natural to ask if the landscape is as vast as allowed by consistent looking effective field theory. We use the universality idea from string theory to suggest that this is not the case and that landscape is surrounded by even more vast swampland of consistent looking semi-classical effective field theory, which are actually inconsistent. And then he suggests that the identification of boundary of landscape is a central question, which is at the heart of meaning of universality property of consistent quantum gravitational theory. So what I would like to tell you is that indeed, there are some non-trivial boundaries of landscape, at least in the context of ADS-CFT correspondence. And I'd like to tell you a little bit about those boundaries. So, I'm going to use ADS-CFT. So that means that I will be only talking about gravitational theory in Einstein space. Ideally, I'd like to talk about theory in flat space or expanding universe. And that's, of course, is an outstanding question. But for now, I would like to tell you what I can do it. And so you consider gravitational theory with negative cosmological constant. And ADS-CFT correspondence says that this gravitational theory in D plus one dimensional ADS is equivalent to conformal field theory in D dimension. So whatever you said in conformal field theory can be translated into gravitational theory and vice versa. So in some sense, we can use conformal field theory as a definition of quantum gravity in ADS. And so what I would like to show you is that there are several what you may call swampland conditions, which is basically the boundary of landscape of gravitational theory in ADS, which are not necessarily obvious. Of course, if you are clever enough, you say, well, I should have known it. But there are certain things that are non-obvious. So I'd like to discuss some of these. So in fact, so this was proposed by Cameron Buffer 20 years ago, and there have been two big threats in the series of swampland conditions. So one is the absence of global symmetry, and the other the claim that there are no adjustable parameters. So So let me just briefly say, so I have talked quite a bit in the past few years about absence of global symmetry, so I will be very brief about it. And so perhaps the absence of global symmetry is the second oldest Swampland conjecture. So this was proposed by John Wheeler and appeared, for example, in writing with his paper with Minsner called Classical Physics and Geometry. So in a more modern way of saying it, it says that if you have quantum theory of gravity, there are no global symmetry. So I would like to see whether this is the case and so this is something that I showed with Daniel Harlow. And in fact, this was a citation of Frontier of Science Prize last year. And so I'm very honored to come back and briefly mention this. And so since I have already given many talks, including the talk at ICBS last year, so I'll just be very brief, but I want to mention a little bit about what I'm thinking right now also. So basically, the proof of absence of global symmetry that Daniel Harlow and I did makes use of the sort of very some logical similarity or analogy between holography of quantum gravity and quantum error correcting code in quantum information theory. So in both cases, so in ADS CFT, you relate information in ADS to conformal field theory. And in quantum error correcting code, what you want to do is to encode information about encoded in logical qubit into physical qubit. And so there is a map from logical qubit into physical qubit. And in ADS CFT, you encode information about local excitation of ADS into CFT theory. And this actually have lots of important implications. And one of the important insights of quantum information theory is Easton-Knill theorem. And that puts some constraint on how symmetry can act on quantum error correcting code. So what basically what this theorem says is that it forbids quantum error correcting code to have continuous symmetry which acts transversely. By that, I mean that, so in the physical qubit, you have a copy of Hilbert spaces like that. And then suppose for each one of them, you have the action of a unitary group. Suppose you want to implement some symmetry. So here, actually, the theorem is about continuous symmetry. So suppose you have continuous symmetry that acts like that. And then you also want the similar kind of unitary group action on the logical qubit. And ideally, if the quantum error correcting code has symmetry, it should commute. Namely, that action of unitary group on the logical qubit should be reproduced by action of this product of unitary group on the physical qubit. And but then their theorem says that it's not possible to do that. If you do that, you cannot encode information. So Daniel Harlow noticed that this is implied by Neta theorem. In fact, when we were writing this paper, we didn't know about this Easton-Knill theorem, and we ran about this after the fact, and then we realized that actually what we were doing is very much in parallel with what Easton-Knill was doing. So basically, what we realized was that, well, if you have symmetry in conformal field theory, then there is a Neta theorem. Neta theorem says that whenever you have symmetry, so for example, well, let's first consider a continuous symmetry. So if you have continuous symmetry, the Neta theorem says that there is actually a local current, which is divergenceless, and whose integral of the exponential of integral of Neta density implements the symmetry. So as such, if you have a spatial Cauchy surface like that, maybe it's kind of awkward, so I'll just do this. So if you have Cauchy surface, so this is supposed to be the boundary of ADS. And if you divide the boundary into non-overlapping segments, then of course the Neta charge is expressed as sum of Neta charge associated to these individual segments. And then, so therefore it's sum of Neta charge is the sum of these contribution from each. So that means that the Neta, that means that unitary operators that implement the symmetry should be product of this. And in fact, there is actually a theorem in algebraic quantum field theory that this is also true in discrete symmetry too, under certain conditions. There are some non-trivial elements of the action of edge between these boundaries. So that makes the proof a little bit complicated. But if you don't like it, then we can also consider geometry like that, which are asymptote to ADS, where we don't have to worry about this. But in any case, the main point is that symmetry is local in this and acts locally like that. So this is very much like this instant Knudsen theorem situation, where if you think of each of these regions as physical qubit and information about local excitation as logical qubit, then basically that if you assume that ADS gravity has global symmetry, then it is the same as saying that symmetry acts transversely. And that's basically the contradiction. Because, for example, if you have local excitation in the middle of ADS, and if you act symmetry like that, then Ryuta-Yanagi surface associated to this each region only acts in this shaded region, none of which touches this one. So that means that this would not work. So one more sort of intuitive way of saying it is that since the symmetry group acts individually on physical qubits separately, so it won't change the entanglement structure between different physical qubits. And however, as we learned in the last 10 or 15 years, that the way that ADS-CFT works microscopically is to use entanglement between different regions as a resource. So and then you reconstruct the bulk. And so therefore, if you have an action that's acting on individually on each qubit, the physical qubit, then it won't act non-trivially on the bulk. So it cannot be a symmetry in ADS. So that's sort of the idea of the proof. Yeah, well, I went very quickly about this because I have already mentioned this earlier. By the way, I noticed that the clock is turned off, which means that I will have indefinite time to talk. I need to find out actually what time it is. Maybe I can take out my iPhone because that's very trustworthy. So I'm 12 minutes. So I think I'm actually on time, so I'm fine. So this was what I did with Daniel. I have a few comments. I have a 2-page comment about this proof. So the idea is that this type of action is inconsistent with expectation that symmetry should act non-trivially on the gravitational field. So a few comments. One is that argument work for spontaneously broken global symmetry also. So that means that shift symmetry, suppose you have a massless scalar field in the bulk, and then suppose the potential is flat, then there is a shift symmetry. But this theorem says that this shift symmetry should be eventually broken. And so this idea also generalized to p-form symmetry and symmetry with Hooft anomaly too. I think it would be very interesting to generalize this for non-invertible symmetries too. This works only for gravitational theory which contains basically black holes. So it doesn't work for 2D gravity. For example, the string worldsheet theory is a 2D gravity. But for example, E8 cross E8 heterotic string is a 2D worldsheet theory of E8 cross E8 heterotic string is a 2D gravity, but you have E8 cross E8 global symmetry. It's an E8 cross E8 gauge symmetry in the target space, but it's a global symmetry on the worldsheet. And so there are counterexamples in low dimension. But this does not provide useful constraint as it is because low energy theory may have accidental symmetry that is violated by high energy. So in order for this kind of theorem to be useful, it should tell us how symmetry is broken. So in fact, in quantum information theory, there is an approximate version of Easton-Knudsen theorem. And there have been actually a series of work. This morning I was just talking to a couple of them. And it's a great opportunity. It has been a great opportunity. So there are some bound on the error by qubit size. And I think we can translate those in the language of gravity. Then we might be able to learn a little bit about. Now, there is also things called completeness of gauge charges that we can prove. And so that means that there are actually, for any representation of gauge symmetry, there must be some particle state. But again, this by itself is not very useful because the we don't know whether the mass of lightest charged particle can be bounded. So unless we quantify those things, it's not very useful. So that leads to the idea of weak gravity conjecture. And there have been lots of attempts to translate that into a conformal field theory language. And some of that seems to have very strong evidence, but I think this is something that would be interesting to explore. Okay, so that's the first thread, the absence of global symmetry. And so I explained why I wrote 1957, because that was the year when the Wheeler's conjecture was officially published. So I'd like to discuss now the second thread, which is that the gravitational theory should not have adjustable. You have a question? Yeah, well, that was one of the motivation for my work with Yuya and Shurdeep also. I might briefly mention this later in the slide, but yeah, so those kind of things can be helpful. Yeah. So the question is how you translate it. So it's kind of related to the question of what kind of charged operator appears. And yeah, so we need to translate that knowledge in the ADS language. So the second thread is the absence of adjustable parameter. So 1949, so that perhaps this is actually the first non-Wilsonian statement that is in literature. And so this is actually appeared in the autobiographical note of Albert Einstein, which is actually very interesting reading. And in one of the chapters of this book, he actually discussed the notion of the natural unit, namely that it's the measure of the unit where you put Planck constant 1, Newton's constant 1, the speed of light 1. And he said that if you use this unit, then the only dimensionless constant could occur in basic equation of physics. So for example, Einstein equation can be expressed in terms of dimensionless constant. Okay? And concerning such, he said, I would like to state a theorem which at present cannot be based upon anything more than upon a faith in simplicity, namely intelligibility of nature, that there are no adjustable constants of this kind. So Kumran and I sort of tried to sort of make this stated in a more modern language. So we made a conjecture that every parameter in quantum gravity is an expectation value of some dynamical field and can be varied by changing expectation value. Okay, so you can ask, well, well, this is a simple enough statement. So if you have a parameter in gravitational theory, is there always some dynamical field which is determined this, okay? So this, we can almost prove this statement. In fact, I briefly mentioned the idea in my summary talk at the String 2022. I'm going to explain to you why I have not written this, and but here is an idea. So suppose you have a gravitational theory, and suppose for simplicity, suppose we know there is a Lagrangian for low energy effective theory, which depends on some parameter lambda. Okay, so you have a one parameter family of gravitational. So it could be that you can write low energy theory as Einstein gravity coupled to matter, and lambda can be a parameter for the mass or coupling constant or whatever parameter. And I assume that you have actually family, so you can vary. Okay, so that's an assumption. Okay, so that means that there's a corresponding parameter in conformal theory, right? And so if there is a continuous parameter, then you should be able to deform it. But then if you deform the continuous parameter, the Lagrangian is changed by the amount, and it's actually generate exactly marginal operator. But now it's a simple exercise. If you just look at the table of ADS-CFT correspondence, you see that if there is an exactly marginal operator in conformal field theory, it's dual to massless scalar field with flat potential. So such that this is determined as a symptotic value. So this is like almost a proof, right? So why didn't I write it? The reason I haven't written it is that actually this is a conjecture in conformal field theory. That is when it's a claim that whenever you have exactly marginal deformation in conformal field theory, there is an exactly marginal operator. Is a conjecture that requires proof. So in fact, Shota Komatsu, Yuya Kusuki, and Marco Marinelli and I are almost finishing a paper where we actually show this. But so let me briefly tell you some idea about this. So actually, the proof is simple if you assume there is an interface. So let me just explain that idea. So consider you have a continuous family of conformal field theory. So you have a conformal manifold, and suppose you choose some parameter lambda. So you compare 2 points in conformal field theory lambda and lambda plus delta lambda. So there are conformal field theory at each point. Okay, and so if there is an exactly marginal operator, suppose first of all, suppose there is an exactly marginal operator, then which generates this deformation, then you can construct a conformal interface by just basically integrating this exactly marginal operator on one side and not the other. And then you can actually go to infrared to construct interface. And so, for example, in 2 dimension, well, for technical reason, I assume the central charge is independent of lambda, excluding Liouville theory, for example. Then you can actually construct the following things. So consider the following things. So suppose you consider 2-point function of energy momentum tensor. Then the residue of the singularity is given by central charge. And the same is on the other side of the interface. But suppose you consider correlation function of energy momentum tensor across the interface, then the 2-point function will have a different coefficient. And in general, this C12 is smaller than C. And you can actually calculate this if you know that this interface is generated by exactly marginal operators, that it's given by pi square times the deformation parameter square. Okay, so it's negative. It's smaller than C. And in fact, you can show that the ratio of C and C12 is reflection energy transmission coefficient. So energy transmission coefficient is less than 1. So, and then the reflection coefficient is the square of the deformation. So that's sort of the statement. So, but you can ask, well, is converse true? So namely that supposing there is a conformal interface connecting 2 points, such that the C12 approaches C quadratically as the variation goes to 0. Then actually you can prove that there is an exactly marginal operator which generates a deformation. Okay, so here is a brief proof. So when you have a interface, conformal interface like that, then you can actually construct what's called displacement operator. So this is an operator which locally displays the position of conformal interface. You have this conformal interface like straight, you can deform it infinitesimally. And that deformation is generated by the combination of energy momentum tensor. You can, of course, expect that it should be something like that because deforming the interface is the same as deforming the geometry. And so therefore, the deformation displacement can be generated by this kind of combination of energy momentum tensor. And but if you use this condition, then we were able to prove that this displacement operator is a linear combination of dimension 1, 1 operator, a dimension 1, 1/2, 1/2 operator. And moreover, the 3-point function of O vanishes. So this qualifies as the exactly marginal operator of conformal field theory. And for a while, we are puzzled why we cannot get rid of this. But there is actually a logical possibility that there is actually also a continuous family of interface itself. And so this operator actually generates that. So in all, this reconstruct the exactly marginal operator. And this actually proof generalized to higher dimension. This proof does not necessarily use Virasoro symmetry. So this can be generalized to higher dimension. And but here we are postulating existence of exactly marginal operator. So the existence of conformal interface. So you can say that, well, assuming conformal interface is almost like assuming that the value of the moduli can be deformed locally. So I take that. So we are also making progress improving existence of exactly marginal operator without assuming conformal interface. So that's why this is not, we have not yet published a paper. But I think we are making good progress in actually nailing this. So that's what we are doing. I have one more comment about this subject, which is that this absence of a just parameter in quantum gravity sounds very much like absence of global symmetry in Wheeler's case. And in fact, there is a logical connection. Because you can think of absence of adjustable parameter as absence of -1 form symmetry, because each parameter in a deformation space corresponds to -1 form symmetry. And I didn't go into detail of discussion. Well, actually, I did mention this. So essential feature of the proof is a Noether theorem that you can split the symmetry generating operator into product of operators. So if you have that, then you can prove absence of global symmetry. In this case, zero form symmetry. But absence of adjustable parameter is almost like that, because what essential feature, essential idea being used in this proof of absence of adjustable parameter is that the deformation is generated by local operator. So I think that if you think about it, it's actually you can recognize this as actually the splitting property of -1 form sigma. So there is actually a connection between these. Okay, so you see that the conjecture zero of Cameron and I, that every parameter in quantum gravity is the expectation value of dynamical field and can be varied by changing expectation value, is almost provable in the context of ADS-CFT correspondence. But unfortunately, just like absence of global symmetry, this itself does not provide useful constraint, since what appears to be adjustable parameter in low energy theory may be fixed by potential in a more fundamental high energy theory. So for example, we know that standard model of particle physics has 19 parameters, or 7 more parameters if you include the mass of neutrinos, or lambda CDM model of cosmology has 6 parameters. And we don't say that those are in Swampland. And so they just may correspond to some dynamical field, but somehow, for some reason, their value can be fixed by some high energy physics. So we want some more quantitative conditions. So Kumran and I proposed some additional conjecture. One is that on the parameter space, there is always the infinite distance direction, such as, for example, in Calabi-Yau compactification, some non-compact direction, which opened up the internal space. And but typically, at least in all examples that we have looked at that time, that if you go to this infinite distance, the low energy effective theory is broken with the emergent tower of light particles. And we actually conjecture that this light particle emerges exponentially. The mass is bounded exponentially in the distance. And so that's, we conjectured, and then that was like 19 years ago. And since then, there have been, many people have studied many examples. And at least in supersymmetric Calabi-Yau compactifications, that no counterexample have been found as far as I know. And the way that this light particle appears has clarified quite a bit. So more mathematically, the statement can be formulated in the following way. The conjecture zero, as I said, is that every parameter in quantum gravity is an expectation value of a dynamical field and can be varied by changing expectation value. The conjecture one said that choose any point in a moduli space. For any positive phi, there is another point, p, such that the distance can be arbitrarily large. And the conjecture two said that compared to this original point, the theory at the very far distance has infinite tower of light particle, starting with mass of order exponential alpha phi for some other. Okay. So this is a little bit more quantitative version of the original conjecture zero. Well, ideally, we would like to bound this parameter alpha, because we would like to know how quickly this light particle appear. So this is actually the recent progress. So so this, as I said, these two conditions that we conjectured have been tested in many examples in string theory, and no counterexample, as far as I know, have been found. And they can impose sharp constraint in low energy Lagrangian, especially if alpha can be bounded. So this is something I would like to tell you about today. So in fact, in the context of ADS-CFT correspondence, this has been translated in the language of CFT by Eric Perlmutter, Leonardo Rosselli, Cameron, and Irene Valenzuela a few years ago. And I might have put the date wrong, actually. But the conjecture one says all points in higher spin symmetry are at infinite distance. And the conjecture two is all CFT at infinite distance are higher spin point. And amazingly, this conjecture 1 has been proven full generality in higher dimension, conformal field theory space-time dimension 3 or higher. But what's not known is the general constraint on alpha. For example, so how this is the case. So that's what I would like to do. So with Ifan, who is sitting at the front row, last year we wrote some paper where actually we are able to put some sharp bound. So this general, they formulated this conjecture for d equals greater equals 3 or greater because the situation in 2 dimensions is different. So we actually focused on 2-dimensional case. So in that case, actually, we can say something very quantitative. So let me go through this. So the first statement is that if there is a geodesic conformal manifold along which conformal dimension vanishes in some limit, then the homological distance to the limit is infinite. And in that limit, this conformal dimension, which is supposed to vanish at that point, vanishes actually exponentially. And we can actually bound this both above and below. And we can also quantitatively see what kind of, how this divergence, the light particle appears. So, so this I thought was very interesting. And so this was very crowded page. So just to encapsulate what the statement Ifan and I proved was that in 2-dimensional conformal field theory, the conformal dimension can vanish as you move along the conformal manifold only at infinite distance measured in the Morozov metric. And the way it vanishes like exponential with alpha, coefficient alpha bounded both above and below. See the central charge of conformal field theory. Okay, so this is actually interesting because if the CFT, 2-dimensional CFT has a holographic dual, then in fact you can translate everything in the ADS unit. And then in fact in this case actually alpha is sandwiched between Planck scale and ADS scale. So we can see that actually you can see the onset of light state in the Planck scale. So if you can think of this as a gravitational theory in ADS with some scalar field, then you go the infinite distance and the scalar field becoming light. And you can ask how fast it can be. We can say that at least in the Planck scale, we can start seeing the onset of light particle. Okay, so more precisely, when scalar field travels in distance greater than Planck scale, the tau of light particle must emerge. And but if it is greater than ADS scale, that it can emerge. Okay? So that's the sort of. And so in the remaining time, well, actually, I have a few more things to say, but I would like to tell you a brief idea of the proof. So start with a simple case when there is only one exactly marginal operator. Okay, so this is a simple case. And once you understand this case, it's a generalization to multimoduli case is straightforward. So suppose there is a primary field phi, O. The O is a primary field whose conformal dimension vanishes at some point. So assumption is that there's a point in conformal manifold where conformal dimension of some operator vanishes. So I call that operator O. Okay, and so let's choose a geodesic to that point. So then renormalization group equation says that the variation of the conformal dimension is given by 3-point function of that operator with exactly marginal operator that generates a symmetry. Okay. And so then you can see that the distance to that point where delta vanishes diverges if and only if this 3-point function vanishes linearly in delta, at least linearly in delta. Okay, and in fact, we can show a stronger statement that we can prove that this 3-point function vanishes, in fact, linearly in delta, and in fact, with coefficient 1 in the 1 modular case. So that means that by substituting this into here and integrating, you see that you have delta, dd delta is basically proportional delta. So even high school students can integrate this equation and find that the delta vanishes exponentially with coefficient 1. Because how do you prove this? Well, so the trick is, so you want to prove that the 3-point function vanishes, but in fact, rather than saying that it vanishes, if you actually write the derivative of this operator, you can actually extract some current operator whose conformal dimension would like to be 1. Okay, so this is actually easier to prove. And this operator J becomes actually dimension 1, 0, because this operator O becomes dimension 0, 0 in the limit. Okay, so now, so I want to prove this. Okay, so let me present a simple but less rigorous proof. In our paper, we actually gave some kind of, for pedagogical reason, gave this proof first, and they gave a more precise version of the proof. And but for the sake of time, I'm just going to give you a simpler but less rigorous proof. And if you are rigorous quantum field theorists or bootstrap people, you might complain, but we can discuss that later. So the idea is that, well, if you have if you have operator, conformal primary field, whose dimension is delta, we know two-point function is like that. So if you define derivative of O as J, then you can actually calculate two-point function J like that. There is JJ, J bar, J bar. They look as if in the neighborhood of delta goes zero, as if dimension 1, 0 or 0, 1 operator. But there is a mixed correlation, and it's trying to vanish in the limit of delta goes to. So anyway, so it's like that. So the idea is to use the bootstrap equation. So you consider 4-point amplitude, the J bar J, J bar J. And then in the T channel, actually, you have this identity exchange. And so it's factorized like that. In the S channel, there is an identity exchange. And next one is exchange of exactly marginal operator. And then there are other operators. But here's the miracle of two dimension, which is that if you look at the conformal block of exchange of identity in the T channel, it's exactly the same functional form as the exchange of marginal operator in S channel. So actually, you can compare this. This vanishes. So therefore, you can compare, by comparing this in the limit delta goes to 0, CJJM should go to 1. Well, in fact, well, this square is 1, so you can say it's plus or minus 1. But you can choose a direction to go to, if in distance, to choose a sign to be 1. And so then delta goes to exponentially 0. Higher dimensional generalization is very straightforward. And so the corresponding equation here, I assume that there's only one exactly marginal operator. But suppose there are more marginal operators, then you have to sum them up. So equation becomes like that. Some of them are exactly marginal, some of them are not. So by taking these into account, you can show that the coefficient is now less than 1 because there are directions goes to other directions. Okay, so other inequality can be proven by the consistency of operator products expansion and the unitarity. So anyway, so this is what we proved. So so far the summary is that we have related these two things, and I think that it will be very interesting to understand also whether this connection between absence of adjustable parameter and absence of global symmetry, this unification of the two constraints can be generalized also to the relation between distance conjecture and weak gravity conjecture. And there is a reason to think about that, because you see that both of these are, again, quantification of these conjecture. Well, these are now theorem, at least in the case of ADS. But these are quantification of these theorems in the sense that for example, weak gravity conjecture quantifies the way that the charged particle appears. So no absence of global symmetry means that you don't have global symmetry in ADS, but you can have gauge symmetry. But then when you have gauge symmetry, there's the completeness theorem. So there must be a charged particle. But then this quantifies how charged particle should appear. Again, the absence of adjust parameter can be quantified to the distance conjecture, but then there is this coefficient alpha. And then Eve and I just proved that this alpha there is an interesting inequality for alpha. So it has a very similar flavor as weak gravity conjecture inequality. So I think there must be something to it, and it'd be interesting to understand the connection. So this is actually the main thing I wanted to tell you. But one of the things that I think it helps is to understand the notion of distance in conformal manifold better. So if you have conformal manifold, of course, there is a homology of distance. But there are other possible way of defining distance, and understanding this connection would be very interesting. And in fact, this was proposed by Mike Douglas maybe 20 years ago or so. That so here, for example, in our proof of existence of exactly marginal operator, we made use of conformal interface. So you can ask, well, suppose you have two conformal field theory, we are connected by conformal interface. could that be used as sort of defining distance? And so if there is actually a nice way to define distance, you may be able to define also distance between conformal field theory which are not continuously connected. So then this would sort of unify the understanding landscape of conformal field theory more broadly. So another thing I have been doing for the past few years is to understand property of conformal interface better. So I'd like to spend maybe the remaining 10 minutes or so telling you about this. So now this is for something completely different. If you are over 50, you know what this is. If you are less than 50, below 50, you don't need to know this. But anyway. So one of the things that I found fascinating is that there are actually many universal properties of quantity that characterizes conformal interface. So when you have conformal interface, there are a variety of quantities that characterizes. One is this two-point function of energy momentum tensor. Let me write it over here. So suppose you have an interface, and suppose you have a conformal field theory on this side and this side. Then you have, if you have energy momentum tensor over here, this is Z, this is W, then it goes like C over 2 over Z minus W to the fourth. But suppose you have U, then you can also consider T of Z, T of U. Then it goes like CLR over 2, Z minus W to the fourth. And then, for example, C left right over C gives you energy transmission. So it's supposed to be less than or equal to 1. And there are other quantities that characterizes this. Well, so there is also, so first of all, this C left right should be less than conformal dimension. In general, C left and C right can be different. So let me just write it. So here, for example, I can have C of left, for example, and you can have corresponding quantity on TU, TZ to be C right over 2 of U minus B to the fourth, for example. And then there is this inequality, but there is something in between them, which is called the effective central charge. And that sort of control the entanglement across shifting. It's another interesting parameter. And we found some interesting inequality between them. So I'd like to tell you about that. So as I said, this ratio of central charge across the interface and central charge on either side is related to the energy transmission coefficient. So therefore, the requirement that energy transmission is less than or equal to 1 give rise to this inequality, which was known many years ago. So now there is another notion called the effective central charge, which is related to the entanglement entropy. So suppose you have a two-dimensional conformal field theory. It's very well known that if you have a segment of length L, then the entanglement entropy is given by log of the distance, the size of this interface with coefficient given by central charge. And if you have interface that goes across the interface, then it's basically the sum of conformal dimension on the left and conformal dimension on the right. However, if the entangling surface ends on the interface, then there's actually different quantity. And in fact, it was not known whether this C effective and this C effective were the same quantity, which required proof. And so first we proved this one. But then there is this actually very nice inequality, which we were able to prove by generalizing the proof of C theorem by Cassini and Huerta. And so basically, Cassini and Huerta used this kind of a triangle inequality of some variation to prove the C theorem. But what we did is basically some variation of their proof with one end of this triangle to be one vertex of the triangle to be on the interface. And from that, we can actually prove that by applying strong subadditivity, we can prove the inequality that we desire. And there is also lots of evidence for the upper bound, which we checked with the holographic example and free field and its variations. So look like there is this type of inequality between effective central charge and C left right. And as I said, this side is proven by strong subadditivity. This seems to hold for both holographic CFT and free CFT or the perturbation thereof. The lower bound means that the amount of energy transmitted across interface cannot exceed the amount of information transmission. So this is sort of rather counterintuitive. So this means that in order to transmit energy, you need to transmit information. Usually we say it in the opposite way, that we say that in order to transmit information, you need to transmit energy. But here, when you have a conformal interface, it seems like it works opposite way. And it's been interesting to understand the physics implication of this type of inequality. And also, I want to mention that these inequalities are actually sharp. You cannot improve it because we found the example of CFT where it's saturated this. And so I think that there are, this is interesting. I eventually would like to prove inequality on this side. So that's another story I wanted to tell you. And finally, more recently, and this is, related to the another entanglement inequality that another entanglement quantity, which is generalizes entanglement entropy called Renyi entropy. And there we were also able to derive some universal properties. So I think there are lots of interesting universal property of conformal field theory that you can derive by using interface and their properties. So anyway, so this is what I wanted to tell you. I'm leaving 15 minutes for questions and comments. So, but I thought it'd be good to end the talk with some sharp equations, or in this case, inequalities. And one is that there are actually two main results I wanted to tell you about. So one is my work with Yifan that the conformal dimension of operator decays exponentially with the two-dimensional coefficient can be bounded in this way. So this can be sort of you can think of it as quantification of the distance conjecture in the case of ADS that Kumran and I proposed. And I forgot to say that these inequalities are sharp, that we have an example which saturates both. I have already told you that the alpha, when you have one moduli, alpha is actually one. So this shows that this upper bound cannot be improved. The lower bound is a case when conformal the limit is actually the decompactification limit, and C is dimension of the decompactification. In that case, this inequality is saturated. And the second point was that, well, of course, it was known from the time of the work by Penedones and collaborate, and even going back to Runkel in 2006, I think that this CLR and the central charge are related by this inequality, but we can actually refine it by inserting effective central charge in between. And this seems to have lots of interesting physics implications. Okay, so that's all I wanted to tell you. Thank you for your attention.
So, any question?
Thanks for a very interesting talk. I think it's probably, I mean, I'm a mathematician, so I think it's probably challenging to define CFT with interface rigorously. So I'd like to know if there's a non-trivial example you can tell me about, CFT with an interface.
Well, so for example, so you are a mathematician, so I need to know what kind of non-rigorous statement you can tolerate. So for example, are you okay with Gaussian conformal field theory in two-dimension whose target space is a circle?
Yeah, that's fine.
Are you okay?
Yeah.
So one example of conformal interface is suppose you have a conformal field theory whose target space is a circle of radius R1. So for example, you have CFT1, CFT2, and you can have here circle of radius R1. And here you have a circle of radius R2. Okay? So these are two conformal field theory with the same central charge, C equals 1. There can be an interface between them. which interpolate. And then the condition for the interface is that the combination of Virasoro operator on this side is equal to combination of Virasoro operator on this side. I might be wrong with the sign, but it's something like that. So you will impose this type of condition on the interface. Now, I can make this a little bit more rigorous. You ask, there is no known example of rigorous definition of interface. I would like to challenge that claim. So the idea is the following. So there is a fairly rigorous definition of conformal field theory with boundary. And the idea is that if you have conformal field theory, suppose you so this is CFT. So suppose it's 1 plus 1 dimension, but Euclideanize it. And then suppose you go in one direction and it stops somewhere. Okay, so namely that you want to define conformal field theory in half series. Okay, and but here's the state propagating. So that means that in order to define this boundary, you just need to specify some state. Okay. It is not in the Hilbert space, but I can make this in the Hilbert space by multiplying some small amount of Virasoro operator. So this is in the Hilbert space. B itself is an extension of Hilbert space. But if you multiply this, then it becomes element of Hilbert space. And this one, I can actually construct it in a fully explicit way. For example, in this example of conformal field theory circle. In general, this can be expanded in terms of very well-defined set of states called Ishibashi state. Which can be expressed in terms of some of descendants of Virasoro representations. And so I think this is fairly explicit. And if you know how to do this, do you think boundary CFT is mathematically well-defined? But there's various version of mathematical rigorous construction. To some extent, okay. Now, to that extent, whatever that is, then I can also construct interface, because the idea here is that suppose you have interface, suppose you have CFT1, CFT2, I can fold this one. So I can fold this one. By folding, what I mean is that suppose you have a Hilbert space of conformal field theory 1, Hilbert space of conformal field theory 2, then I consider another conformal field theory, tilde, which is whose Hilbert space is tensor product of H1 times H2 bar, where H2 bar is given from H2 by parity conjugation. So then you have actually a conformal field theory with boundary. And this interface condition is exactly the same as conformal boundary condition. So if you agree that in certain cases, the boundary conformal field theory has a rigorous definition, then the interface also has a rigorous definition. Right. That's correct, yeah. Yeah, no. I do agree that this state that I would need to construct is not in the Hilbert space. Its norm is divergent. But the actual calculation you want to do are the operator located away from the boundary. And there you can actually use regularized version of boundary states, which are in the element of Hilbert. And then if you move this to the boundary, this local operator typically diverges in the way that is expected from the fact that these states are not in the Hilbert. I hope it makes sense. At least a fraction of what I said makes sense. But yes, in the back. Speak up or use the microphone.
Okay, I have a naive question about the correspondence. Say, let's just say in the large n limit, we say
what did you say?
In the large n limit.
Large n limit.
Yeah, for ADS-CFT. And we know there are infinitely many CFTs interacting or free series, but the symmetry dictates that.
Sorry, I didn't quite understand. Say it again.
Okay, sorry. I mean the symmetry of CFT constraint that the dual geometry can only be pure ADS, right? I mean in higher dimension, not ADS3 CFT2.
So there are many examples of ADS2, ADS3 CFT2 examples where large N limit gives you a gravitational theory. For example, the famous example is the two-dimensional supersymmetric sigma model, whose target space is a tensor product of K3. And suppose you have n tensor product of K3, you orbifoldize it by action of a symmetry group acting on the exchange of these K3. And that has a gravitational dual as type 2b string theory on ADS3 times S3 times K3. And large N limit is a supergravity.
Yeah, but my question is for higher dimensions.
For higher dimension, well, so n equal 4 super ion mirrors is dual to type 2b on ADS5 cross S5.
Yeah, okay.
I'm not sure I understand the question, but
I
but if you are
communicate
satisfied,
after
I'm
the
happy.
talk.
Yes, please. Yeah. Let me go back. Yeah, this is a kind of my favorite subject. So, yeah. So like that. Right? Oh, in which examples? Oh, well, that's what you said sounds very interesting, but probably, are you talking about it in particular mathematical construction in the context of some? Okay. H0, what space? Yes. Okay. Ah. Oh, yeah, I see what you mean. Oh. Oh, okay. Why that? Oh, so you can quantify the failure by the amount of the eigenvalue of Laplacian. Yeah, okay. Ah, okay. Well, that's very interesting. I haven't thought about it this way, but it sounds like it can be useful point of view, actually. Yeah, so thank you. Yeah, I haven't thought about it in this way, but I guess in this case, we are considering space of conformal field theory. So I think that the notion of this, so you're considering some geometric object, I presume, and you consider H0 and H1. So I need to think what would be the analog of that. So then I need to know what the H0 and H1 for conformal field theory. Maybe there is some notion like that we can cook up, and maybe that's what I should. Yeah, but thank you. This is I want to understand this better. So any idea in that direction is very helpful. So thank you for saying. I'll think about it.
Any other question?
So in one of the slides, it was mentioned that at infinite distance, we have emergent free scalar sector. Is there a simple reason why it cannot be a more general non-complex CFT like Liouville theory?
So sorry, say it again.
So at infinite distance, where the gap closes, Is there a simple reason why we cannot have some other non-complex CFT other than just free boson, something like Liouville theory? Is there some intuition for this?
Well, so what Eva and I did, and in fact, so I didn't have time to explain it, but and then in fact it was suggested by, say, for example, Konsevich and Soeberman earlier also that so they actually claim that if you go to infinite distance in CFT, it's always the decompactification limit in the case of T2 dish. That's what you are referring to?
Yes, yes.
Yeah. So Eva and I almost prove it at least locally in the context of conformal system. Locally, in the sense that, for example, you can have non-compact limit of orbifold, or you can have a limit where target space of conformal PVC can have wall, and the distance between the wall becomes infinite or something like that. But if you look at the target space structure, so so what I say is that if you take this limit, then we can actually prove that in the limit is always some conformal field theory with target space, sigma model, whose target space is locally expanding. And that's, I think, is true statement, if I is here to compare. But I guess you are suggesting there might be more possibility.
Yeah, I was wondering whether it can be maybe something like the Liouville.
Yeah, but Liouville is we are not including. So this was, so we always have to read small points. And I'm not sure whether I can get to the small point, but I said that central charge does not change by lambda. So in the Liouville theory, central charge changes. So that case is excluded. Yeah, Ifan had some comment.
So it's time to stop here. If you have any other question, please talk to the speakers privately. And the next talk was dead at 2:15. Let's thank our speaker again.